we have V is equal to W over Q. Now this W over here is work, unit, joules, energy. So W is equal to V times Q. Alright? Now Q is charge. Q is equal to IT in terms of a formula. Alright, it's your charge times your time. Your I is equal to your Q over your time. So I can take this Q and replace it by IT. So I get W is equal to VIT. Alright. Power is equal to work over time. It's a rate of doing work. Alright, so work divided by time. So power is equal to W over T, or VIT over T is equal to VI. So power is equal to V times I. Alright, a very important formula. Probably the rivaling the R is equal to V over I, because in actual application we use this a lot, that your power is equal to your V times your I. You can work out the power of any appliance and so forth that's being used. Now just to go from there, so I have power is equal to V times I. I have got V is equal to I over R. Do I not? No, I don't. I've got R is equal to V over I, so V is equal to I times R. Alright? So I can replace my V here in this formula by IR, and I get power is equal to IR times I, and that's I squared R. So that's another way of writing the power formula as I squared R. Okay? And I've also got, if I wanted to take this a little bit further, I've got I is equal to V over R. So I can take my formula here, this power, and I can replace my I this time. I can replace my I by V over R, and I can get power is equal to V over R, so that's V squared over R. So I have three formulas that I can use for power. Power is equal to VI, or power is equal to I squared R, or power is equal to V squared over R. Three formulas, and you'll find all three of them in the data booklet. Okay. Now all of them relate to power. Alright. Which is the energy per unit time. And that's how things are always given to you when you look at an appliance. I've got my kettle here, and we've used this kettle before, and it's got a power rating, and I'm going to say this power rating is 2,400 watts. So I've got my kettle. For my kettle, it says that it's got a power rating. Power is equal to 2,400 watts. Now what does that mean? Alright, so when I switch my kettle on here, click, it's starting to use straight away 2,400 joules every single second. Alright? It's a lot of energy. As I said, a joule is not all that much. Alright? Remember, it takes 4,200 joules to raise the temperature of water by only 1 degree Celsius. It takes a lot of energy needed, you see. So I can hear the noise coming up here. It's starting to make a noise. That's the energy coming in at 2,400 joules every second, being changed into heat, which is heating up the water. Alright. Now, we buy electricity. The school is going to have to pay for that little thing that I did there. Alright. They're going to have to pay for it. Alright. A certain amount of money, because that electricity came from the municipality, Prague municipality, which buys electricity and then sells it to us, but through the electricity company. Alright. Now they sell electricity or power or energy by using what we call the kilowatt hour. The kilowatt hour, or the kWhr for short. Basically what that means, if my kettle was instead of a 2,400 watts, say it was a 1,000 watt, it's one of those really slow kettles that takes forever to heat up anything. It's 1,000 watt. If I switch this on and I let it go for an hour, alright, I use it for an hour, the amount of energy that this kettle would use in an hour would be a kilowatt hour. It's the amount of energy used by a 1,000 watt appliance in an hour. That amount of energy is a kilowatt hour. So let's just calculate it. 1 kilowatt hour. Alright, so you've got a 1 kilowatt. How much is a kilowatt? It's 1,000 watt. Alright? Which is 1,000 joules per second. Alright? And it's for an hour. Alright? So that is going to be in seconds. We're going to have to multiply that by 60 times 60. That gives me 60 times 60 is 3,600 times 1,000, 3,600,000 joules. That corresponds to a kilowatt hour. When you go to your electrical meter outside, you will see that they are the units there on kilowatt hours. That means every time it clicks over, you've used 3,600,000 joules of energy, and Prague will charge you for that. They will say 15 crowns, please, for every kilowatt hour of energy that you use. So when you run your bath, for instance, and you're working on an electric or water heater, that's going to cost your parents some money. Alright? So when they tell you don't use too deep bars, if they ever do, I don't know if they ever do that. You know, for families that are a little bit more financially stretched, perhaps, they will be worrying about that. They will be saying, you know, because that's where most of the energy actually costs. So this is the amount, and this is the kilowatt hour. Alright, does that make sense? Okay. Now, just by way of this, the electricity that we get is 240 volt electricity, I think, here. 240 volts. It means that all the V is, your potential difference is 240 volt. 230, it varies. Like this one is varying from 220 to 240. I'm using 240 because I said that my power rating on here, my power rating was 2,400 watts. Therefore, according to this formula that power is equal to VI, I can work out the current that's going to be going through here. Alright? Because it's 2,400, this is 2,400, this is 240, that must be 10. So I have got a 10 amp current, which is quite a large current. Now I've got to make sure that my cable can handle that, otherwise we can have a burning experience. The cable that you have needs to be able to handle a 10 amp current, which is quite large. So that's why, for instance, the wire that is going to charge my computer here is relatively thin. Alright? The current here is also, the potential difference is also 240 as it goes in. You'll notice here actually when you look at this is a transformer here. We're going to learn about transformers more in the high level section. But this wire here you can see is thicker than this wire here. Alright? This wire is using 240 volts. Alright? And it's got a certain current. That's the input current. it needs the output that it's giving out is a different voltage and a different current, but it's thinner because it's less, you see. So you have to be, when you're working as an engineer, when you're designing equipment and so forth, it's very important to make sure that the thickness of the wires and so forth, all your resistors and so forth are lined up, that they can handle the currents and so forth that you're dealing with.